Okay, good afternoon. It's my great pleasure to introduce Kevin Hand, who is a scientist at the Jet Propulsion Laboratory. And his dream is to put a lander on Europa. And he'll describe that to you in a minute. Kevin got his undergraduate degree at Dartmouth in psychology. And then he got a master's degree in engineering at Stanford University. And then he got his doctorate in geology at Stanford University. So he's gone from a shrink to a rock. Anyway, Kevin has been working at JPL now for, I don't know, at least 15, 16 years, at least, right? So, I'm going to leave the rest to him because he gives great talks. Thank you, Kevin.
Excellent. Thanks, Paul. And slight amendment to that. I got undergrad degrees in physics and psychology. So the physics and astronomy was primary. The psychology was an added bachelor's, primarily focused on my interest in extrasensory perception and communication with possible communication with alien life forms. I think the movie Arrival. But in any case, my primary focus was physics and astronomy. Apologies that I can't be there in person. I really would have loved to have been there. And I hope to get to Rutgers in the not too distant future. Paul and I talk here and there about me coming and spending some time, and I really would love to do that. And Janice, great to hear all the EPO work. Fantastic job, and please let me know if I can be of any help with that. Always happy to give virtual presentations. Those are easy, and anything I can do to help with stronger links with NASA or JPL, et cetera. Happy to do that. Okay, let me dive in here. So shameless plug, the title of my talk is the same as my book title. I've recently published a book called Alien Oceans, The Search for Life in the Depths of Space. It's out from Princeton University Press. It came out in April of 2020, which was quite unfortunate because, as we all know, that's when COVID was just starting to run rampant. So all of the talks and media and that stuff got canceled. But nevertheless, I encourage you to check it out. It's a labor of love that goes through not only the exploration and understanding of worlds like Europa, Enceladus, and Titan, but also a lot of history of the exploration of our own ocean. And so I really tried to bridge worlds beyond Earth with our own planet. And so speaking of which, we have been exploring our solar system for just about 60 years now. The Mariner 2 spacecraft that flew by Venus was launched in 1962. And since that time, many of our missions have gone out to the moon and to Mars, several to Mercury, many around the sun, but very few spacecraft have made it beyond the asteroid belt. The few that have are named Pioneer, Voyager, Galileo, Cassini, and more recently, the New Horizons and Juno missions have gone out there. And by merit of the exploration of these few spacecraft, we now have good reason to predict that oceans are common in our solar system. And shown here is a portrait of the ocean worlds of our solar system, or at least the worlds that I and many of my colleagues are quite confident have oceans. Now, of course, at the center is the Earth's ocean, the ocean that we know and love and need to protect. Around the Earth, I've placed Europa, Ganymede, and Callisto, 3 moons of Jupiter that are covered in ice, and beneath their icy shells, we have good reason to predict that liquid water oceans persist today. I've also got Enceladus and Titan, 2 moons of Saturn. These are worlds which also have liquid water oceans beneath their icy shells. In the case of Titan, there's the added curiosity of its thick methane-rich atmosphere, and on its icy surface are lakes of liquid methane and ethane, driving a methane hydrological cycle. And I've even got Neptune's curious moon Triton here. The evidence for a subsurface ocean there is not quite as strong as these other worlds. But nevertheless, with that limited information, it's sort of hard to explain away an ocean on Triton. There may be other worlds that also have oceans, but for now, these are kind of the 6 primary ocean worlds. And these worlds with their subsurface oceans are really transforming our understanding of what it takes for a world to be habitable. As we all appreciate in the early days of planetary science, there was this kind of Goldilocks configuration for the habitable zone. And it was well defined by Venus, Earth, and Mars, where Venus was too hot to have a liquid water ocean on its surface, Mars was too cold, and Earth was in the perfect Goldilocks zone. Now, of course, the story is much more complicated. Venus has a very interesting past, Mars has a very interesting past, but at least in the modern epic and the rough outline, in order for a planet to have a liquid water ocean on its surface, the general thinking was that you had to be at that 1 AU, that 1 astronomical distance, so as to maintain and sustain a liquid water ocean in contact with a nice thick atmosphere. But these ocean worlds of the outer solar system are teaching us that this is an old Goldilocks. There's a new Goldilocks in town where the energy to maintain and sustain liquid water oceans comes not from your parent star, but rather from the tidal tug and pull that worlds can experience as they orbit giant planets like Jupiter and Saturn and Uranus and Neptune. And there's no better example of this new Goldilocks for habitability than the 4 large moons of Jupiter. And shown here is Io, the innermost large moon. Io is kind of like Venus in this analogy. Now, Io does not have an ocean. Io is, however, the most volcanically active body in the solar system. And it is so volcanically active because it's getting tugged and pulled and stretched through the tidal interactions it has with Jupiter and the other moons. Meanwhile, at the outer edge, Callisto is kind of like Mars. Callisto, we think, may have an ocean, but our understanding of the tidal energy dissipation there is still very limited. And if Callisto does have an ocean, it may be more of a slushy layer that's sustained through radiogenic decay. In the middle, Europa and Ganymede, and Europa in particular, may really occupy this new sweet spot, this new Goldilocks region, where it has just the right amount of tidal energy dissipation so as to maintain that liquid water ocean. In the case of Europa, we have reason to predict that it's about 100 kilometers deep, 60 miles in depth. And that ocean is underlain by a rocky, silicate-rich seafloor, and it's overlain by an ice shell of H2O, of water ice. And that ice shell is comparatively thin. And by comparatively thin, I mean it's on average perhaps 10 kilometers in thickness. It might be a lot thinner in some places, a lot thicker in others. But for the most part, that generally agreed upon number is about 10 kilometers or so. And what that means is that the ice shell of Europa may serve as a window into the ocean below. And Europa has very few impact craters, which to a planetary scientist means that it's a young surface age. In the case of Europa, we estimate that its surface age is somewhere between 10 and 100 million years old. In other words, comparable to the age of the oceanic crust in the depths of our ocean. To give you kind of a sense of scale of how much tidal energy is available on these worlds, there's the Earth, where our oceanic crust average ranges from about 60 to 80 milliwatts per square meter. Io, again, no ocean, but the most volcanically active body, is upwards of 2,500 milliwatts per square meter. A tremendous amount of energy from that tidal tug and pull. Europa, we have poor constraints on, but it's somewhere in that range of 10 to 800 milliwatts per square meter. In other words, it could be an order of magnitude more active than Earth's seafloor. And then in Enceladus, we have this south polar terrain where there's a lot of heat pouring out of a very specific region, and that amounts to about 16 gigawatts, which then averaged over the surface leads to about 200 milliwatts per square meter. And we're still trying to understand the dynamics there. Now, you might ask, if you're an orbital dynamicist, well, how can these moons sustain tidal energy dissipation? Typically, over billions of years, worlds synchronize and they circularize, and there's no more real tidal tug and pull, no more actual dissipation that's occurring. In the case of the Jovian system, there's a really beautiful resonance that occurs. It's called the Laplace resonance, and it's a sort of, kids on a swing set pumping each other. And in this case, Io, Europa, and Ganymede all orbit with a resonance where for every 2 times that Io goes around Jupiter, Europa goes around Jupiter once. And for every 2 times that Europa goes around Jupiter, Ganymede goes around Jupiter once. And this means that the alignment, as shown in that diagram in the middle, leads to each of these moons pulling on each other so as to maintain a forced eccentricity in the radial tides. And that's what helps sustain this tidal energy dissipation through time, preventing the orbits from just circularizing and becoming kind of dormant from a tidal energy dissipation standpoint. Now, the Saturnian system is quite a bit more complicated. There are a lot of mid-sized moons and smaller moons, and there have been a lot of resonances through time. At present, Enceladus and Dione are currently in a 2-to-1 resonance. But there's a lot of head scratching when it comes to figuring out exactly what is happening with tidal dissipation in the Saturnian system, and in particular with what's happening with Enceladus. This plot that I'm showing from Meyer and Wisdom in 2007 shows time in billions of years going back in time, and looking at how various resonances between the moons may have occurred. Now, I'm not going to go into detail on this, but suffice to say that in order for Enceladus to be a primordial moon, the quality factor, the tidal quality factor for Saturn and Q, this tidal quality factor is kind of a to call it a fudge factor would be harsh, but let's I've got the definition of it down there. It's a real challenge in planetary science trying to figure out how moons and planets stretch and dissipate tidal energy and friction. But suffice to say that for Enceladus to be primordial, Saturn needs a very high Q. With that high Q, you then cannot explain a lot of the heating at Enceladus. As I mentioned, Enceladus has got this south polar region that's expelling about 16 gigawatts of energy. And so if Enceladus is primordial, then we have this problem of the Q factor being too large to explain the heating. However, more recent publications have argued that based on archival data, we can see sort of a tidal recession from telescopic observations and Cassini observations. But that leads to a much lower Q of order of in the range of 1700. To have a Q so low, however, requires the moons, including Enceladus, to be very young, of order 100 million years. And this is a real puzzle. This is kind of where the community is at with respect to understanding Enceladus and its evolution. And so if, in fact, Enceladus is 100 million years old, the question arises, would life have had enough time to originate, and would Enceladus actually be a stable enough world for sustained habitability? And this image at right, that's Tethys and the rings of Saturn. And just to kind of put this conundrum into context, the rings of Saturn are telling us part of this story. There's long been a debate about the stability of the rings of Saturn, because typically a large planet like Saturn would clear out the rings in a relatively short amount of time. One nice thing about this second hypothesis, this lower Q hypothesis, is that it helps explain the rings as a result of some kind of cataclysmic impact event that occurred, say, 100 million years ago from an object from the outer solar system, a Kuiper Belt object perhaps, coming in and hitting a moon or other object. So still a lot of debate about what exactly is happening at Enceladus, but that's an important one in the context of habitability. if Enceladus is young, is it in fact that attractive from a habitability standpoint? Okay, coming back to the Goldilocks kind of framework, along with liquid water being sustained through tidal energy dissipation, we can consider other frameworks for Goldilocks, the availability of elements, both light and heavy. And we've seen various permutations on the periodic table. This one we adapted from Wackett et al. 2004. I won't go into detail on this, but suffice to say, we all appreciate that life as we know it needs the light elements, the carbon, hydrogen, nitrogen, etc. And one could reasonably argue that Earth is a bad place for life when it comes to the light elements. Earth did not retain much in the way of the volatiles. The inner solar system was kind of baked out. That's why we have the rocky planets. That's why we've got Mercury, Venus, Earth, and Mars relatively dehydrated. And as I'm sure many of you have heard, some of the contemporary thinking on Earth's oceans is that it was something, the water was supplied through cometary impacts and perhaps wet asteroids coming in to supply upwards of half the water that we have on the surface of the Earth. But in the outer solar system, these icy moons of the outer solar system, the retention of volatiles is not a problem. These are regions in our solar system where the snow lines, the ice lines for condensation of everything from water to methane to ammonia and so on and so forth are well surpassed. And so when these moons formed, it was easy to accrete a lot of those light elements. And I'll just kind of simplify this diagram here, where everything above any given compound line here is retained as solid ice. If you're below the line, then it sublimates off eventually. And you can see that for Europa and Enceladus, they're so cold that they can retain carbon, sulfur, nitrogen, rich compounds like HCN, ammonia, etc. And for Titan, the pressure is high enough that you can actually also retain out a lot of methane. So these alien oceans, these icy worlds of the outer solar system are great places for the light elements that are needed for life. What about the heavy elements? Well, this diagram, I think, captures that aspect quite well. On the y-axis there, of course, is density, how dense these moons are, and then radius. Let's start at the upper right, the densest of the satellites, the rocky satellites. Io and the moon, of course, I mentioned Io, no ocean, but very volcanically active. Io and the moon, lots of rocks. Europa, interestingly, is sufficiently dense so as to perhaps be qualified as a rocky satellite. And that's good because, of course, you want not just water and the light elements, you also want those heavy elements that life needs. And so having a sufficient amount of rock, being sufficiently dense, is important. Meanwhile, if you get too far down to the bottom left, now your density is so low that you might have too much ice and too little rock. And there you can see Enceladus, very small and relatively low density. Now, we do think Enceladus has at least some silicate interior. It's likely not differentiated. That's still a topic of debate. But when it comes to that water-rock interaction, at least from a density standpoint, Enceladus is quite low. Then I'll just touch on some of the larger satellites, the larger radii satellites, Ganymede, Titan, and Callisto. These moons are particularly curious because you get to such a size and mass that you might have a fair amount of rock. But in these worlds, you have not only an ocean covered in ice, but the pressure at the base of your ocean is sufficiently high so as to yield higher phases of water ice, things like ice 4 and ice 6, etc. And so in other words, you end up with oceans of liquid water potentially trapped between two ice shells, an ice shell at the bottom and an ice shell at the top. And that might not be good for water-rock interactions. You might not have leaching through silicates, et cetera, that supplies you with the heavy elements for life. And so we're still trying to understand a lot of what those dynamics are like. But let me zoom out for a second and just provide a little more of the high-level motivation. All of these alien oceans, these ocean worlds of the outer solar system, are incredibly compelling targets in our search for life beyond Earth. I would argue in large part because of the prospect of finding extant life. I need to sip my tea here. They offer a place where we could potentially find extant life. And this is in contrast with our search for life on Mars. On Mars, and I love Mars, I'm a member of the Perseverance team, and we're collecting cores to bring back to Earth. It's incredibly valuable. But the rocks that we're examining and bringing back to Earth from Mars are billions of years old, and we have no expectation that any of the large biomolecules are going to be retained in that. We don't see, of course, any DNA, RNA, or even proteins for that matter in Archean rocks on Earth. We have no expectation that such molecules would survive in the rock record on Mars. And so we might find biosignatures, we might find isoprenoids, hopanoids, steranes, kind of remnants of lipids from various membranes. But finding the true information molecules and what makes life on Mars tick, I would argue, is going to be quite challenging. But these alien oceans where liquid water exists today, life could also be alive there today. And that's much of what motivates my interest in these worlds, is the prospect of finding extant life where we could perhaps explore this prospect of separate independent trees of life, and possibly even looking at the chemistry that drives them. Do they run on DNA, RNA, proteins, or is there some other game in town? And this is really interesting because it presents the opportunity to kind of look at comparative origins, contingent versus convergent chemical evolution. Within the Earth origin of life community, there are several different paradigms: the primordial soup, the Miller-Urey hypothesis that has many different threads to it these days. There's the hydrothermal origin hypothesis, and also a little bit of work on cold and icy origins, an area that I love. And then planetary transfer, but I don't like that because it's of little utility. These ocean worlds of the outer solar system give us an opportunity to look at a second data point and perhaps learn more about modalities for the origin of life. And as an example, Europa, Enceladus, there are no continents there. There are no tide pools. There's no shores of continents on which waves can lap and the sun can bake things. So the primordial soup hypothesis does not work for Europa. That means if we were to discover life on a world like Europa, that would point to hydrothermal origins or a cold, icy origins. And coupled with that, these ocean worlds of the outer solar system are much harder to seed with Earth life. And so even if we were to find DNA-based life there, I think we might be able to take a step towards concluding that that's indicative of convergent evolution towards DNA as a prime biomolecule for biology. Whereas if we found, let's imagine we found extant life on Mars in the subsurface someday, if it was based on DNA, we, I think, would have to be very parsimonious and conclude that it was perhaps related to life on Earth, because we are near neighbors and material gets thrown back and forth quite frequently. So just to give some context for how to categorize these different worlds, I place Europa and Enceladus prime among this kind of new Goldilocks. Titan is a great place for weird life, in part because it's got this other solvent, the ethane lakes on the surface. Ganymede, Callisto, and Titan, from a subsurface ocean standpoint, might be too big and the ice might be too thick. There are worlds that might be classified as relic ocean worlds. The asteroid series amongst those, and Mars, of course, at one time had a surface ocean, and then Triton and Pluto kind of classify as unknown. And there's just for Titan a little graphic showing that liquid water ocean perhaps trapped between phases of ice. Okay, so that provides a bit of an overview. I'm now going to get into quite a bit of detail about Europa, and I'm going to have to move a bit fast. So apologies, hold on to your seats. Europa orbits Jupiter some 318 times as massive as the Earth, and Europa is about the size of our moon. I'm not going to go into detail about how we think we know the ocean exists. I'll just say, please read the book. There's a chapter on each of these 3 easy pieces in the book. And what those 3 easy pieces lead to is this kind of framework for Europa: this ice shell, this ocean, and this sea floor. Now, one of the things that's been very curious about the ice shell of Europa and has been a topic of debate is what is causing this discoloration that we see on the surface. Europa is predominantly water ice, but then when we look at its surface, we see this reddish, yellow, brown kind of material that is coincident with a lot of the fractures that we see. And in the early days of the Galileo mission, the spacecraft that flew by Europa back in the late 1990s and early 2000s, there was a great debate about what the spectroscopy was telling us. And shown here is one of those spectrums, the NIM spectrum there shown in bold. That's the near-infrared mapping spectrometer that was on Galileo. And early on, there was thinking that, wow, this spectrum matches a frozen magnesium sulfate brine relatively nicely. You can decide for yourself how sufficiently well matched that magnesium sulfate is to the NIM spectrum. But there was a simpler hypothesis that was put forward that the dark material that we see on Europa is in fact sulfuric acid hydrate. And you might say, well, how is that a simpler hypothesis than the magnesium sulfate brine? Well, the magnesium sulfate brine hypothesis for matching the spectra implicates a salty liquid water ocean. And while that's very attractive, it's also quite an extraordinary hypothesis. Meanwhile, the sulfuric acid hydrate has quite a simple explanation, and that is that Europa's innermost neighbor, Io, shown here, is spewing out all of this sulfur from all of its volcanoes, and that sulfur then gets entrained into the plasma and magnetosphere of Jupiter. And here's a little cartoon that I drew ages ago showing Jupiter at the left and then Europa in the middle there. And Europa gets bombarded by electrons and ions as Jupiter's magnetic field sweeps past it. And so sulfur ions from Io's volcanism impinge on the surface of Europa, and the radiation processing with the water ice on the surface then quite easily leads to H2SO4 hydrate. And so that explanation for the dark material on Europa is quite solid. We think that at least some of the material on Europa is derived from that exogenous sulfur and then radiolytically produced sulfuric acid hydrate. The magnesium sulfate hypothesis is, in my opinion, still has quite a few question marks on it, not the least of which is that I think it's actually hard to maintain a magnesium sulfate ocean. If you're in fact cycling with a silicate seafloor, you're more likely to have a sodium chloride ocean than a magnesium sulfate ocean. That third bullet point, my colleague Mike Brown and I, a number of years ago, took some ground-based spectra. We came up with an alternative hypothesis. I'm not going to spend time on that today, though I think it is still quite compelling. Really what I want to focus on is something else altogether. And that brings us to my lab out at JPL, the Ocean Worlds Lab, which I should mention, I love getting interns, and in particular, I'm a big fan of having interns not during the summer. it's a little bit easier actually to get work done during the school year. So if there's any students looking for research projects that want to come out for a week or two or what have you, lots of opportunities, but I try and steer more towards the calendar year. Maybe you can work on a thesis project or something. So in any case, in our lab at JPL, we've got various vacuum chambers where we can recreate the pressure and temperature and irradiation environment of worlds like Europa and Enceladus. I refer to this as our Europa in a can. And so we can cook up things and look at what happens. And for the case of the discolored material on the surface of Europa, I was particularly curious about the sodium chloride hypothesis. I alluded to this earlier. If Europa does in fact have a long-lived liquid water ocean in contact with a rocky seafloor, then just by analogy to our own ocean, it should follow the same residence timescales for various elements. And as we know, in our ocean, NaCl is a predominant salt because of the residence time and lack of drawdown of those two elements as cycling occurs between the ocean and the seafloor. So if Europa's ocean is long-lived, it should be dominated by sodium chloride. Let's look for sodium chloride spectroscopically. Well, that's where you encounter a problem because, as we all know and appreciate, sodium chloride is just flat white. It's table salt, of course, and spectroscopically, it is just flat also. There are essentially no useful features. And you can see it at reagent grade sodium chloride on right there. However, when you put it in a chamber and start irradiating it, I don't know if this actually has a little bit of sound of it, but it's just the sound of my pumps and stuff in the lab. When you irradiate sodium chloride and pull it out, it turns to an interesting yellowish brown, and depending on how long I leave it in, reddish color. And what's happening here is that alkali halides like sodium chloride trap electrons in what are called F and M centers. It's really interesting quantum mechanics that I don't have time to get into today, but a lot of the early work on this connected back to the simple harmonic oscillator and various S&P excited states of the trapped electron. So really interesting work that kind of traces the early evolution of quantum mechanics. But for the sake of finding oceans, salty oceans elsewhere in the solar system, I want to focus in on the spectrum. And so through the irradiation, these electrons get trapped. The salt turns a yellowish brown color, and you also get these very distinct absorptions. In this plot here, I'm showing you various spectra of irradiated salts, grains, evaporites, grains with water. And at the top, you can see NaCl grains with no irradiation. You can see photolized sulfide, and you can also see the magnesium sulfate. And this is all in the visible part of the spectrum. The color bars there correspond to the Galileo camera filters, which were a useful first attempt to try and see whether or not the colors on Europa match these distinct absorptions from the F and M centers. But the color filters were not of sufficient resolution to really nail this down. However, Samantha Trumbo, who at the time was a grad student at Caltech, and I worked with Samantha and Mike, her advisor, to see if we could get some time on Hubble. And Samantha led the effort to get us some spectra from the Hubble Space Telescope. And sure enough, when we got the spectra back, and you can see them at right here, our jaws just dropped. We see this very distinct absorption. So the red line here are my lab spectra, and then the black is the Hubble data of Europa from this particular region. And as you can see, this 450 nanometer feature, which corresponds to the irradiated sodium chloride, very well explains the absorption that we're seeing on Europa. And down here, you can see the map of essentially intensity of the depth of that feature across Europa. So through this observation with Hubble, we think we really nailed down the fact that at least some of this discoloration on the surface of Europa is due to salt NaCl coming up from the ocean below and then being exposed to the radiation environment on the surface of Europa. And I like to think of it kind of like invisible ink, where without the irradiation, you cannot see the sodium chloride, but with that irradiation, it becomes very distinct and easy to pick out from the spectroscopy. I want to touch on just a little bit about additional irradiation chemistry. And there's a very curious aspect of Europa's ice surface temperature, and that is that it ranges from about 70 Kelvin to 130 Kelvin in the day-night cycle. And this is interesting because the OH radical goes from essentially being immobile to being mobile. Now, really, it's the electron that's moving around in here, but as you warm up the ice from that nighttime temperature of Europa to the daytime temperature, you can get a lot of radical chemistry occurring. And in the case of pure water ice, that irradiation leading to radicals, leading to radical recombination, etc., yields hydrogen peroxide and oxygen. And on the surface of Europa, we actually observe both hydrogen peroxide and solid phase O2. And that's really interesting. Obviously, much of the ENIGMA team is very interested in the history of oxygen on Earth and what that implies for both pros and cons with biochemical evolution. Well, here on Europa, the radiation environment yields an abundant source of oxidants, everything from sulfate to condensed phase oxygen. And if that oxygen made on the surface is in fact cycled into the ocean below, you can actually relatively easily get to concentrations of oxygen that are well above the oxygen levels found in the O2 minima zones in Earth's oceans. And that, of course, is exciting because on Earth you see polychaete worms and other organisms that survive in those regions. So Europa may be conducive not just to microbial life, but should Darwin permit, perhaps the oxygen levels are sufficient to allow evolution to proceed to more macroscopic organisms. Just kind of as a little bit of a circuit diagram for possible metabolisms, I put this together a number of years ago. In gray are the compounds that we know exist on the surface of Europa, the peroxide, the oxygen, elemental sulfur, sulfate, water, and carbon dioxide. From the seafloor, we can expect a number of other things, but this is kind of a rough sense of what might be possible. And in the case of thinking about a biological ocean, there are sort of three different scenarios. If a lot of the tidal energy on Europa is dissipated in the ice shell, then you might have very efficient cycling of oxidants into the ocean below, in which case you might have a highly oxidized ocean. If, however, most of the tidal energy is dissipated in the mantle, then you might have less efficient delivery of oxidants from the ice, but more efficient exhumation of reductants from the seafloor, and then you might end up with a reduced ocean. And in the third case, you might have a balanced partitioning of tidal energy dissipation in the ice and in the mantle, so as to lead to a delivery of oxidants and a delivery of reductants that can sustain biology through eons. And these are kind of three predictions that I have for the state of Europa's ocean. So just looking at time here, I think what I'll do, let's see, Paul, we're at 10:45. Let me just, there's a bunch of stuff that I can come back to on the fate of carbon and nitrogen on Europa. So perhaps we'll do that during Q&A.
You have about 10 minutes, okay?
I do? Okay, I wasn't sure if just given the later start. Yeah, okay, let me come back since we got so many chemists in the room. I'm going to breeze through this because this is particularly interesting, and this is my bread and butter in terms of what I do in the lab. So very quickly, you can think about the fate of carbon, and I've done experiments where I've irradiated water and carbon dioxide. And the long and the short of it there is that you produce a lot of carbon monoxide and carbonic acid. So if you just have CO2 and water, that's what you're going to get. I've also done a slew of experiments with various 3 and 4 chain carbon compounds, looking at the survival of sigma and pi bonds, et cetera. You can read all about that in this 2012 paper. And what's interesting here is that along with producing CO2 and methane, you do relatively efficiently destroy the double bond, but you actually get a lot of polymerization. You form formaldehyde and then alcohols, and then you end up with kind of a Europa tholin. And even after heating up the ice and letting all of the volatiles release off into the chamber, I'm left with residues. You can see the residues on the gold mirrors that I use at the end of the cryostat, and those microscopic views of those organic residues there. And examination of those, I just see these incredibly complicated long-chained aliphatics and aromatics, which again, not too surprising. We see this in the interstellar media. But one of the interesting consequences and predictions on this is that if Europa has no organics and just carbon dioxide, then the kind of canary in the coal mine spectroscopically is going to be that carbon monoxide. Meanwhile, if organics are present in the ice, I did not see much carbon monoxide in the irradiation with hydrocarbons. The added hydrogen scavenges the CO to then form the formaldehyde. And so if organics are found, we will not find associated carbon monoxide. We'll instead see that polymerization through the HCO plus H chain. And very briefly, adding nitrogen, adding ammonia to the system, things start getting quite interesting. I can form formamide quite easily, and I even have some compelling evidence for diamino. I can never pronounce this, so I'll just call it DAM. The acronym serves quite useful in this case. And both formamide and DAM are very useful precursors, both for nucleobases and for amino acids. So some quite interesting chemistry, prebiotic chemistry that might be proceeding through the surface irradiation of Europa. By comparison with irradiated microbes, there is actually hope for teasing these apart. I've looked at a lot of abiotic chemistry shown there in black, and then I've also irradiated microbes. And this is where Paul and I have talked about taking some of the proteins and other molecules that many of you are generating and putting those in the vacuum chambers to look in more detail at some of the specificity of what I've seen in some of my earlier experiments. And here with the irradiated Bacillus pumilus, what persists are the amide bonds from the beta-pleated sheets and the protein structures that do not get completely destroyed. So there is a way to distinguish abiotic from biogenic chemistry. Okay, and I'll finish with just a little bit on the future. This is Europa up close. This is the highest resolution mosaic that we have of Europa's surface. At the finest scale here, we're at about 6 to 10 meters per pixel. The cliffs that you see here are about 100 meters or so in height. This is a grayscale image. All of the black and grays that you see here would likely be red or orange or brown in color. And they may be deposits that have salts or possibly organics or possibly even European shrimp. So what's next? Well, the Europa Clipper mission is slated for launch in 2024. I'm a scientist on that. The European Space Agency Jupiter Icy Moons Explorer, aka JUICE mission, is slated to launch around the same time. Both missions will get to the Jovian system in about 2030 and start really exploring Europa and Ganymede and the other moons in the early 2030s. Coupled with that, we've also got the Dragonfly mission, which is headed to Titan. I'm a science team member on that mission, and this is an astounding mission where we're going to parachute in and then octocopter down to the surface and then fly around Titan's equatorial region to explore the dunes and chemistry of Titan. And as Paul mentioned, my real love, my real passion is getting down to the surface of Europa with a lander. I've spent much of the past 15 plus years at JPL working towards this mission. It's a very, very mature mission concept. We've already spent over $300 million on the development of the mission. We've passed through our mission concept review and our Delta mission concept review, built lots of hardware, prototypes, many different things, had various calls for instrument development, and have a very detailed science definition team report. Unfortunately, the Planetary Science Decadal Survey just recently came out and prioritized a Uranus orbiter probe, which is great. I'm happy for that. My friends who are very interested in that. And it's the second priority was an Enceladus Orbilander, which again, Enceladus is a wonderful world, but that mission wouldn't even go to the launch pad until 2037, and it wouldn't land until 2051. Meanwhile, while Europa was in the flagship mission list, we could launch as early as 2030 and arrive at Europa in the 2035 timeframe. So the Decadal Survey obviously is recommendations. NASA is still considering all of what's in the Decadal Survey, but my hope is that we will proceed with the Europa lander, because this really is a fantastic mission to follow on the Clipper mission, to which NASA has already committed. It's a much lower risk mission than doing something like an Enceladus Orbilander that has got a lot of technologies that haven't even been built yet, such as next generation RTGs. And in this mission, as you can see in this animation, we would utilize a modified version of the Sky Crane with terrain relative navigation and hazard avoidance. Our Europa lander project actually invested in the Mars Perseverance landing. We helped pay for a lot of the terrain relative navigation. So that's now proven. Once we're on the surface of Europa, this is a battery-powered mission. We could live for as long as 90 days with the batteries. That's comparable to the Mars exploration rovers. It's nice not having radioisotope power sources because they are a huge challenge from a planetary protection standpoint. So that's part of the reason we went primary batteries instead of RTGs. Once we're on the surface, the spacecraft would deploy a robotic arm that could excavate as much as half a meter or more into the surface, getting below any radiation processed region. And then it would deliver that nice handful of snow and ice to the vault, the chassis of the lander, where it would then get analyzed by a gas chromatograph type instrument, a Raman spectrometer type of instrument, and a microscope type of instrument. And I say type of instrument because were the mission to go forward, we would have an announcement of opportunity, and those slots for different instruments would be competed. Along with those three instruments, there's cameras and a seismometer package. The seismometer package would listen for Europa quakes and give us a better sense of the ice shelf thickness and the depth of the ocean. So I'll finish there, and hopefully we have time for a question or two.
Thank you very much, Kevin. That was a great talk. I'm opening up to questions. Vic?
Thanks, Kevin, for a great talk. What is the temperature of the ocean in Europa? And the reason I ask is because with proteins, when we do crystallography on proteins, the glass transition is around 150 Kelvin. And below that, you wouldn't have any activity, even if they are folded. And if it's another polymer, you might change it by a few dozen Kelvin, but they're all going to sort of freeze out below 150 or so. So is that still a functional range for polymers?
Yeah, so that's really interesting. That I didn't know that 150 Kelvin for proteins. We should brainstorm on some interesting experiments to do there. From the standpoint of the ocean itself, though, once you're in the ocean, the environment there is quite benign. Just by this curious quirk of physics doing what physics loves to do, and our solar system doing what it does. At the depth of Europa's, so Europa's water is in the range of 0 Celsius to 4 degrees Celsius. Of course, 4 being the densest, the temperature of greatest density. By merit of being liquid water, it's got to be in that range of 0 to plus or minus maybe 10 degrees C. The salt in the ocean might suppress it by 10 degrees centigrade, but really it's a quite benign temperature for life as we know it. And with respect to pressure, the Europa's gravity is about 1/7 of the Earth. And what that means is that at the depth of Europa's 100-kilometer deep ocean, you are at a pressure that is comparable to the pressures found in the Mariana Trench here on Earth. And so life thrives in those regions. And so kind of a good analog for Europa's ocean, I argue, is these trench environments, because the temperature and pressure down there is going to be comparable to what we find in Europa. So proteins will be fine. I am curious, though, if we think about psychrophiles surviving at the ice-water interface, and whether or not there might be any prospect of proteins being selected for that allow life to thrive in some of the brine and oxidant-rich channels. So maybe some interesting things to explore there.
So I have 2 questions. I understood that there's so much high energy particle bombardment of Europa that you can't put solar panels on the lander. Is that true?
No, so we could put solar panels on it. The Juno spacecraft and the Clipper spacecraft are both using solar panels, and so solar panels have been radiation hardened and are working great for Juno. And the surface environment of Europa is actually a bit more benign than if you're floating out there in space around Jupiter, because once you're on the surface of Europa, you're shielded by Europa itself. Really, Paul, what it has to do with is just the mass of the solar panels. You're 5.2 astronomical units away from the sun, and so there's kind of diminishing returns of how much surface area you need to just get the basic energy you need to sustain the spacecraft, and the complexity associated with folding out solar panels. We could do solar panels instead of RTGs and instead of primary batteries, but it's a big mass and complexity hit.
Okay. So the second question I have, and I'm sure you've done these calculations, how far down in the ice do you have to go before you don't destroy all the organics on the surface of the ice?
You mean by irradiation on the surface?
Exactly, radiation and peroxide.
Yeah. So the actually, let me see. I think I have an extra slide. Yeah, perfect. I'm going to show a plot of this. So the first thing to appreciate is that not all regions of Europa are irradiated equally. And so here's a map projection of Europa's surface. The equatorial region shown here in blue indicates the region where charged particles being swept past Europa through Jupiter's magnetosphere and plasma, where those particles predominantly hit. This is kind of like a runner in the rain, where the rain is sweeping your backside, and a little bit occasionally you get a gust of wind coming from the front. And so so these equatorial regions are irradiated more intensely than as you get further north and south. Coupled with that, there's a surface age component, because your total dose, of course, it depends on how long the surface has been exposed. And so for a 100 million year surface age, a pure water ice surface would be radiation processed to 60 gigarad dose. That's the equivalent about 100 EV to 16 AMU. That's a bit of an arbitrary number, but in the radiolysis community, that's a number that we've long used, just as saying, like, once you've got 100 EV per 16 AMU, that's enough energy such that if any bond wanted to break, it would have broken. And so at that surface age and for pure water, you need to get down to 10 centimeters depth or deeper. So that's within the blue region for that surface age. Now, with Clipper, we could find that there are fresh plumes and a really young surface within that blue region, and then you only need to sample down millimeters. Or you may find that you want to land out of that region anyway, just from the spacecraft standpoint. But this is kind of a different way of presenting that that data for different regions. And so we designed the robotic arm on the lander to get well below any radiation processed depth, whether it's in that high radiation area or in the more benign regions of Europa's surface.
Thank you very much. Are there any other questions from anybody online? Going once, going twice. So, Kevin, thank you so much. That was a great talk. And Vic and I will be back in touch with you about putting some proteins into your Europa in a can, and to see if you can tell if there's histidine or cysteine that remains after you process it. I mean, or what would be left over of cysteine and histidine, right?
Yeah.
So
looking forward to it.
The fragments of those two amino acids would be very interesting if we could discover them.
Mm-hmm.
They're not, as far as we know, and as far as I know, and maybe you know more, found in any chondritic meteorites.
No, for the most part, it's a pretty boring slew in the meteorites.
Okay, super. Thank you so much.
Thanks.
Bye-bye.